So separating of solutions. Solutions को separate करना in terms of separating the soluble solutes from solutions is somewhat different. ठीक है. इस केस में हम जो biggest property use करते हैं वो boiling point होती है. ठीक है. Boiling point is a very good property that can be manipulated to separate solutions. If I go back a couple of pages, हमारे पास यहाँ पर ये you'd see that in order for us to separate a solid and liquid, and we're talking about the soluble one. I don't know whether you have marked it or not. We are talking about the soluble solid in a liquid. Okay. In case if you want the solid, you use the crystallization process that we have previously explained. It is the difference in solubility. If you want the liquid, if you're interested in that, then you use distillation. I also ask you to write simple distillation instead of just distillation, right?
Yes, sir.
And in the case if you have two liquids in a solution, if they are miscible liquids, then we are going to use another form of distillation, that is fractional distillation. So up next we have both of these kinds of distillation, the simple distillation and the fractional distillation. So let's start with simple distillation first. All right, don't forget that we are talking about the soluble solution and we're talking about separating the liquid. All right. अगर तो हम किसी liquid की solution की बात करते हैं, हम बात करते हैं salt की, तो we do understand that we have the process of crystallization. Evaporation is going to give you the powder, evaporation is going to evaporate the liquid away. But what if you want the liquid? If you want the liquid, you can't go with the evaporation process. You need something else. So there comes distillation. Separating a liquid from a solution is carried out by distillation. How do we manipulate the boiling point property? Boiling point जो होता है liquid का, that is much lower than that of the dissolved solid. ठीक है? So liquid is more volatile. Liquid can be easily evaporated. What this line means is that we can evaporate the liquid much easier than we can separate the solid by heating. All right. So what we can do is that we can evaporate off the liquid, but we can actually collect it and condense it back to a liquid form. That we do by a condenser, water-cooled condenser, and that is separated separately. All right. So what do? Let's understand it from the diagram. It's pretty easy. Take seawater as an example. Now, seawater consists of a lot of salts, plus it consists of water. Now, what are we interested in? We are interested in water. What do? We take an amount of it in a distillation flask. This is also known as a round bottom flask, as the name suggests, right? So we take that flask and on the upper end, we connect a thermometer. The thermometer keeps us a good idea about how high or low the temperature is, or have we achieved the boiling point of the liquid or not yet. What you're supposed to do is to make sure that the bulb of thermometer is right in front of the mouth of condenser. All right. Why? Because this is the point where we need to note the temperature. If the temperature here is equal to the boiling point of the liquid, all right, this makes sure that the liquid vapors rise up and move all the way into the condenser through this tube. Now, this condenser is water cooled. You can see water going in the outer jacket, only this colored part. The water does not go into the inner pipe, right? And when it is outer jacket is filled, the water flows out. Water actually overflows out, which means we completely fill the jacket, and so much so that the water flows from top. This is water out. This comes from a local tap, and this goes to the drain usually, right? So what does the condenser do? The cold water that is coming from the tap actually exchanges the heat with these vapors. The vapors are then condensed back into liquid droplets, which are collected separately. This jacket of the condenser actually is there to just exchange the heat.
Sir,
See?
can you please repeat? आपकी आवाज glitch हो गई.
Okay. So I was talking about that this jacket of this condenser, the outer part of this condenser, has some tap water coming in. This tap water has a colder temperature. This tap water has a normal temperature because inside we have hot vapors coming in. The inner pipe has hot vapors, all right, and the outer jacket has cold water. When they both come in contact through a glass, actually the vapors heat them up, and this in turn cools the vapors. I need to write cools instead of colds the vapor. Cools the vapors, all right? So that's what happens. Do you get the point? It's exchange of heat. Okay, I think you're having a hard time understanding exchange of heat, right?
Yes, sir.
Okay, let me give you a daily life example. Now, in harsh winters, what we usually love are hot beverages. Let's say you like coffee a lot, okay? You're gonna fill up an entire mug, and with that mug, let's say you have a filled mug of coffee. Sometimes what we do is that holding the mug from this end, what do? We wrap our hands around the mug. That actually comforts us in harsh winters. In harsh winters, the weather is pretty cold outside. Drinking a hot cup of coffee feels pretty good. Not just that, wrapping your hands around the mug also gives you a feeling of comfort, does it?
Yes,
Why? Because the hot coffee inside actually gives heat to your hands, right? It gives heat to your hands,
yes,
and in turn, your coffee slowly cools down. So the coffee becomes a little bit drinkable and your hands become hot, which is actually a feeling of comfort at both ends. The coffee
yes,
becomes a little bit more drinkable, easily drinkable, and your hands feel the warmth of the cup, which is actually a comfort in harsh winters. So the same thing happens over here. The hot peppers are cool down because of the interaction with the cold water through a glass. Remember, there is glass surface inside. Just like there was some mug surface in between your hands and the coffee, there is glass surface in between the cold water and these hot peppers. Hot peppers are acting like coffee. The cold water are actually your cold hands because of the harsh winters. So what happens is these hot peppers are going to give their heat to the cold water, just like the coffee gave heat to your hands. And in turns, the hot pepper starts to cool down slowly, right? Which makes the hot peppers easier to drip over here in the form of a liquid. So they don't stay in the vapor form anymore. Easy enough.
yes, sir.
It's just that we're not using our own hands to cool down the vapors. We're using some tap water for the purpose. And of course, the
Jeez.
shape of the condenser is not like a coffee mug. It's totally different.
Yeah,
So I guess from this example, you get the idea of heat exchange.
Jeez, sir.
Good, good. Now, there are a couple of things we need to understand. Whatever we get over here, this product is known as distillate. Remember, we had names of products in filtration process. We have the same
Yes,
over
sir.
here. And whatever we have left over here by the end of the experiment, we call it residue. So it's pretty much similar to filtration. Whatever was left over on the filter paper was known as residue over there. Whatever's left over in the distillation or round bottom flask is known as residue over here. By the end of the experiment, whatever was calculated in the collected in the beaker in filtration was known as filtrate, and here in distillation, it's known as distillate. So our distillate is pure water and our residue is leftover salts. So salts become residue at the end of the experiment and water becomes distillate at the end of the experiment. Make sense?
Yes, sir.
Good, good. If all that makes sense, let me clarify a couple of points. Now, I'm going to erase some of it. I need a few things still written over here, but I'm going to erase the rest of it. Now, The first point that is commonly asked in question is that why the bulb of the thermometer needs to be in front of the mouth of the condenser, because the temperature we need to note, or the boiling point, should be taken for the vapors that are entering the condenser. All right, we need to note their temperature, not the temperature of this solution, not the temperature over here, actually the temperature at the point where the vapors are entering the condenser. That's why the bulb of thermometer
Sir,
is G.
your voice is not clear. It's glitching again and again.
Just give me a minute.
Okay, sir.
So we were saying that the bulb of the thermometer should be right in front of the mouth of condenser. Why is that so? Because the vapors that are entering the condenser, their temperature needs to be noted. We don't need any other temperature. We don't need the temperature over here. We don't need the temperature over here. We only need the temperature for the vapors that are entering the condenser. So the temperature should be noted at this point. That's first thing we need to keep in mind. The second thing, we cannot change the water inlet and outlet points. If we do it something like this, that we take water in from the top and out from the bottom, what would happen is that water is simply going to slide over here under the action of gravity and go out. That is not going to exchange heat. This is not an efficient task. What do we do instead? Instead, we take water in from bottom and we let the whole condenser jacket fill with water, so much so that the water overflows out. All right, doesn't just go out simply, instead overflows, drip out when the jacket is completely filled. That way, water can exchange heat very efficiently. So that's why this setting is there, because it makes efficient heat exchange. All right.
Okay, sir. Yeah.
Good. So these are the two most common questions that are asked from this portion. Apart from these questions, I hope you already understand that by the end of the experiment, this portion will be known as residue and this portion would be known as distillate. And in this specific case, the residue are a mixture of sea salts. There are many salts present in seawater and not just one. And here we'll have water. We like to call it distilled water. Distilled water means the water that has gone through the process of distillation.
Okay, sir.
Good, good. If you understand this, then the whole distillation, simple distillation is complete. Remember, in simple distillation, though we get both the salts and the water, but it was water that we were interested in. We're not interested in salts. It's just the collateral product. It's just the product that we get from, because the process is made in such a way. All right,
Okay, sir.
let's move on.
Yes, sir.
Starting right from this paragraph, separating the liquids from a mixture of two or more miscible liquids is again based on the fact, from this point, we study fractional distillation, right? So if there are more than two liquids which are mixed together and they have different boiling points, then we can slowly boil one liquid after another and separate them first. What would happen? We're going to go for fractional distillation. In fractional distillation, what happens that the most, sorry,
Your voice got glitched there.
I don't understand why this is happening today. Usually that never happens during the meetings. I took a couple of meetings yesterday and they were working fine. Okay. So I was telling you the definition or the way we go for fractional distillation. We go for fractional distillation because different liquids, no matter how miscible they are, have different boiling points. Now, in fractional distillation, which is a good process for separating the liquids that are miscible into one another, we work with the principle that the most volatile liquid, when I use the word most volatile, it means the one that has the low boiling point. All right. that distills over
Yes.
first. And the least volatile, and when I use the word least volatile, I means the one with having the highest or high boiling point, okay, boils over last. It's pretty easy. Let's take an example. Ethanol boils at 78 degrees centigrade, water boils at 100. Let's suppose we have the mixture of two. When we're going to heat them, when we're going to heat this, take a look. Now, this is a solution of ethanol and water. We have an electrical heater. Our apparatus is almost the same, except for this fractionating column, which is different this time. You'd see a long column, and that is filled with small glass beads. And in order to show you the proper diagram, he has given you this diagram. Take a look. It's a column made up of glass, and inside we have small glass beads that we have filled it with. Why? We're going to consider it a little later to understand. Okay. So we fill it up with glass beads. What's going to happen is that as soon as we heat it up, and the temperature around this portion reaches 78 degrees centigrade. Remember, the boiling point of ethanol was 78 degrees centigrade, and the boiling point was for water was 100 degrees centigrade. Now, since there is a difference in their boiling point, we can work with this difference for our advantage. Now, if the temperature is around 78 degrees centigrade, which is the boiling point for ethanol, the ethanol will convert into vapors. These vapors are going to climb up all the way over here and will be able to pass in the condenser. From there on onwards, they are going to drip over here in the form of liquid, and ethanol would be collected over here. But even at 78 degrees centigrade, there would be some vapors for water too. Now, I'm going to draw the vapors of water as blue, right? And the blue is not visible enough. Let's do it with red. So for red, you would notice that the vapors of water will rise up, but at this temperature, they are going to condense and they are going to drip back into the same flask. They won't be able to get over here. Why? Because this temperature is not equal to their boiling point. This temperature is still less and they can be condensed. What helps us to condense is the structure of this entire fractionating column. Now, take a look at this column. If a vapor needs to pass through this column, it needs to go through this like this, right? From this higher surface area, what do? We pack it. When we pack it with these kind of glass beads, it gets a high surface area. A high surface area actually allows the hot vapors at their boiling points, ethanol, to pass through. But for water, what happens to water is that water, if tries to pass, is actually condensed right over here and drips back into the same flask. So ethanol will pass, right? And water would drip back. Make sense?
Yes, sir.
What do? At 70 degrees centigrade, we fill up an entire flask with ethanol. And then if we keep on heating, the temperature would increase. And at one point, the temperature over here would also become 100 degrees centigrade. At that point, it's sure that you have collected all the ethanol in one flask. Remove this flask, put a new dry empty flask over here, and now at 100 degrees centigrade, you can collect all the water over here. So what you can do is that you can do the distillation in fractions, in parts. The word fractional distillation itself means distillation in parts. Every part is known as a fraction, right? So the first fraction was of ethanol. This is the first one that we got in the beaker. And then the temperature increased and we reached the boiling point of water. And the second fraction would be of water. So if we have 10 different liquids or 20 different liquids, we're going to do fractional distillation and we're going to get different parts based upon boiling points. And in every part, we're going to get the most volatile or the lowest boiling point liquid first, and then the next one, and then the next one, and then the next one. Loop goes on until we get the least volatile or the highest boiling point liquid at the end. That's the best part of fractionating column as an apparatus and fractional distillation as a process, that it can separate the liquids which are miscible into one another in the form of different parts, and we call those parts as fractions. Make sense?
Yes.
Now, we're going to move on to the next page, and you'd understand that every part is known as a fraction. It's written over here. Fractional distillation is used to separate any solution that contains different liquids with different boiling points. The liquid in the mixture with the lowest boiling point, which we also call as the most volatile one, always distilled over first. Ethanol had the lowest boiling point, so it distilled over first. The final liquid to distill over is the one with the highest boiling point or the least volatile. Water had the higher boiling point, 100 degrees centigrade, so it distilled over last in the previous example. So fractional distillation can be adapted as a continuous process, and it is used industrially to separate various fractional parts from petroleum, which we're going to study in the second last chapter of this book, chapter number 11 on page 276. And we've already studied how to separate different gases from liquid air. But since this only works with liquid, what do? We convert the gases by cooling them into liquids first, and afterwards you can boil those liquids again to separate them. In case of air, we get nitrogen gas or oxygen gas or argon gas in the same way, right? Which we already have studied. Make
Yes, sir.
sense? If that makes
Yes.
sense, we are done with both fractional distillation and simple distillation. Any questions from these parts?
No, sir. It's clear.
Okay, the questions for fractional distillation have the same ones as simple distillation. For example, why the thermometer, bulb of thermometer is in front of the mouth of condenser, why the condenser water goes in from bottom and comes out from top. These questions remain the same. And then they usually ask the purpose of fractionating column. Don't forget, fractionating column is filled with glass beads. Why glass? Because glass is inert. Glass is unreactive. All right. And why beads? Because they're going to increase the surface area. So it's easier for the liquid whose boiling point hasn't reached to condense right over here and drip back into the same flask. Drip back means come to the same flask in the form of drop by drop as drawn over here.
Sir, can you repeat why beads?
Why beads? Because, and I'm going to mark that right from the book since it's mentioned in the book. Now, glass beads in the column provide a large surface area for the condensation. And condensation occurs for the liquid like water who had a higher boiling point, and it condenses in the same flask and drips back into the same flask. Understandable?
Yes, sir. Thank you.
Good, good. Any other questions?
No, sir. It's clear.
Okay, let's move on to our last example. Since we have less time today, so I'm only going to introduce you to the example. We won't be able to cover it. Now, this book missed the heading. We have actually paper chromatography over here. I give these headings to make it easier for the students that which paragraph relates to which method or technique. Now, paper chromatography starts from here, and I'm going to go a couple of pages back to the table that we started off with. And if you take a look at that table, you'll find that paper chromatography is the last separation technique. We're done with all the techniques. This is the last one we need to go with. And actually, a solution of two or more solids in a same liquid are separated with chromatography.
Okay, sir.
Right? For example, if you have sugar and if you have salt dissolved into a same liquid like water in a same glass of water, if you use these separation techniques, they might not work out. Take a look, we can't use the difference in solubility or crystallization because that would give us the crystals of salt and sugar again. We can't use a separating funnel since they're soluble. We can't use filtration. Again, they're soluble, we can't use it. Magnetism won't work, sublimation won't work, right? They don't have much difference in density to begin with. Decantation won't give us any good since they are soluble. Simple distillation would work to separate the water, but the salt and sugar would remain at the same point. Fractional distillation is for liquids, so we don't need to work it with sugar and salt. So actually, there is no technique which can separate sugar and salt dissolved into the same water for you. So that's why we need this paper chromatography. So again, we can work with solution of two or more solids, which are all soluble in the same liquid. So both sugar and salt are soluble into the same liquid, water. So that's why we need this technique. So moving on, this is the last technique. And let's get back to the same pages. Separating two or more dissolved solids in solution can be carried out by chromatography. Now, chromatography or chromatography has many types. I am using the word paper chromatography continuously because this is the type of chromatography that we are going to perform or learn in our O-level book. This is one of the easiest types of chromatography, and this has a very small, short learning curve which children can adapt to pretty easily. But at the same time, this is going to prove as a very valuable technique. And you would notice when you learn with me that this can be very helpful in not just separating the solids, instead understanding a lot about their natures as well. Now, there are many types, but all follow the same basic principles. Paper chromatography is the simplest form to set up. It's very useful to analyze the substances present in a solution. For example, it can tell us whether the solution has been contaminated with something harmful or not. This can be very important. Contamination is important for us to know in three aspects of life: contamination of food, contamination of drinking water, and any contamination for medicine. These are the three aspects of life where purity is very important, where safety is very important, and anything dangerous can directly affect ourselves. Even our body is not made in the way. For example, if I talk about food, Beta, you might have already read and understood in biology that our mouth is made in such a way that it rejects if the food is not acceptable. For example, let's talk about a sandwich. A sandwich is a common eatable. Let's say it has become stale. The sandwich was out in the air for a few days. Now it is stale. It has a bad odor. There is poor smell coming out of it. You didn't know about it. Intentionally, you took up the sandwich to take a bite. As soon as you're going to get it near to your mouth, and as soon as you're going to open your mouth to take a bite, your nose starts working before you can take a bite. And as soon as you smell that sandwich and you know that there is a bad odor coming, you're instantly going to reject it. If not the smell, the flavor is foul, right? As soon as you put it in your mouth and a foul flavor comes, your mouth is going to reject it. You're immediately going to spit it out, right? This is the most common reaction that happens to us if the food is not good, if the food has been contaminated, it became stale, or it has a foul flavor or smell. Am I right?
Yes, sir.
If, let's suppose, the food was not stale, it didn't have any bad odor, it had nothing like that, and even if you tried to sniff your food, it has such a wonderful smell. Let's say you took a bite of that sandwich. Let's say that part, that specific bite that you took has few grains of sand. And those grains of sand are going to give you a particular sound under the teeth when you're going to chew them. Immediately, your brain would start working, you would know, your mouth would know, and you're going to spit that out again, right? Even if there was no smell, even if there was no foul flavor, but if there were even a few grains of sand, you're going to spit that out. So actually, we are made in such a way that we reject the contaminated food. be it because of the smell, be it because of the flavor or the taste, be it because of anything contaminated inside it that we come to know after chewing, we actually reject that food. Do you understand the
Yes.
point? So contaminations are very important. If we can come up with a technique that can find out the contaminations for us, it can be really helpful, right? So let's talk about a technique like this. Don't forget the three aspects, because they have been a past paper question. They don't ask that question anymore, since they understand the safety. Since after Corona, everyone is more conscious about how they live, how they keep themselves clean, about their food, about their hygiene, about the cleaning of their hands, and the list goes on. So this might not be a question in your paper, since we are more aware now, right? So let's directly jump towards the technique. Okay. So what we're going to do is that we're going to take a strip of paper, and you'd notice some diagrams that they have drawn, and we're going to go through different stages, how to work with that. This is one of the result papers and the B part of the diagram. And then and then we are going to discuss the steps of the process and how we are going to work out the process by using a specific RF formula. But I'm going to do all of that